Okay, I guess we will start now, this morning, and I hope all of the other people will arrive. So I would like to introduce Dr. Peter Kovacs for this first keynote of this morning. You may remember that in my introducing talk yesterday afternoon, I insisted about the profound link between autonomous vehicles and immersive 3D imagery. And I think this talk, and especially the experience of Peter, is a very good example illustrating this. To show you just in a couple of words, to indicate that Peter has got an MSc, a Master of Science in Software Engineering, and a PhD in signal processing, specifically about 3D light field compression at Tampere University of Technology. I was very happy to be on the thesis jury at the time. He has previously spent 10 years at Holographica, and he was focusing on topics such as real-time distributed rendering of 3D data on 3D displays, and please listen, that's capturing with multi-camera systems, real-time encoding, decoding of light fields, calibration of multi-sensor systems, including GPUs, cluster with real-time constraints. And most of these experiences were very relevant to his activity at aiMotive. He joined a little more than 7 years ago, where he's involved in systems of calibrated sensors, which sense the environment at larger scale, capture sensor data, uploaded from vehicle fleet. So you will hear more about that as he's managing this activity at the aiMotive with aiData. He's the senior VP of this activity, and all of this data are captured by the AI teams at the aiMotive. So he was and he is very involved in all of this activity at the autonomous driving, self-driving activity. As you may know, aiMotive was recently acquired by Stellantis. And as part of Stellantis, the tools and technologies developed by aiMotive can be utilized by Stellantis. That's the advantage for Stellantis, but also aiMotive is the benefit for aiMotive that's too involved in the large scale of the 16 brands. Okay, so he will give an interesting talk. Peter, the floor is yours.
Thank you very much for the introduction, András. It's a pleasure to be here. Thank you for the opportunity. And my name is Peter Kovacs. I'm the Senior Vice President of the aiData department inside the aiMotive. And today I'm going to talk about how 3D data processing enables autonomous driving development. Indeed, 3D data occurs in many fields, including automated driving, as well as light field 3D displays, where my previous experience comes from. It's fair to say that during my whole career, I've been working with 3D data basically in one way or another. So I will draw some conclusions between the 3D display world and the automated driving world. Automated driving is practically a robotic challenge in which vehicles are operating inside the 3D world. And in order to do that, they have to sense the world around them with multiple sensors, including cameras, radars, ultrasonic sliders, and so on. And some of these sensors do have depth sensing capabilities, while others don't. But what's very important is that when we have a multi-sensor system, they have to be calibrated in order to produce a consistent 3D representation of the 3D world. This is quite analog to light field capture, where we have been using multi-camera systems to capture the 3D environment, sometimes combined with depth cameras alongside the color cameras. Then, autonomous vehicles must operate in real time because they have to react in real time to the changes in the environment. And in order to do that, they typically rely on GPUs or dedicated neural network inference accelerators in order to be able to execute the neural network models which are typically used nowadays for recognizing the environment. And also, in order to provide redundancy, they typically use multiple compute units in order to provide that redundancy. The analogous example is light field rendering, where you expect the 3D display to update the screen in real time. So real-time operation is also important in that area. Now, if you want to have neural networks to operate inside the vehicle, you have to create them one way or another. And this is the process we call neural network training. This is the process which creates the neural network, which will in turn be executed in the vehicle. This again requires a large amount of synchronized, calibrated multi-sensor data, but as well, it requires reference outputs. So basically, to train the neural network, we have to show it reference input and reference output. And also, the neural network training process requires an interconnected system of GPUs in order to finish in reasonable time. These systems that we nowadays use for neural network training have very similar requirements and almost the same architecture that we have been using for rendering 3D light fields in real time back then. And then 3D data generation. So as I said, the input-output pairs have to be generated either in a manual or automatic or an assisted way. Now, automatic methods, in our experience, rely on a combination of neural nets and classical methods, again, relying on GPUs in order to accelerate the processing of data. Even though real-time operation is not a requirement in this case, still, it's nice to execute them fast in order to be able to crunch the sensor data coming in from many vehicles. Now, in case of light field 3D displays, 3D content creation was always a hot topic where we can get 3D data that we can visualize on the screen. Some examples include CT and MR scans or CAD designs or simulations for that matter. While in case of the automated driving world, 3D data mainly consists of 3D bounding boxes of the objects around us together with their attributes and velocities, as well as road and lane information in the form of HD maps. For those who don't yet know aiMotive, a few words about the company. The company was founded in 2015 by László Kishonti, who is still the CEO of the company. And our company is based in Budapest, Hungary, where the majority of our 200+ people are working. And aiMotive has been working independently through all these years up to the end of last year when Stellantis acquired aiMotive. And this brought one major change, that AI Drive is now exclusive to Stellantis, contributing to the development of the Stellantis auto drive system. Through all these years, we have seen at least 3 generations of different perception pipelines. In the first generation, the industry have been using classical computer vision models, occasionally combined with generic 2-dimensional neural network solutions like semantic segmentation, instance segmentation, 2D bounding boxing, or classification. So basically, we have been reusing what was available in the literature at that time. And also, we used quite generic metrics to evaluate the quality of our results, which basically meant that we estimated the pose of the positions based on the 2D detections and projecting them back to 3D. And also, we had to manually resolve the differences between the world models experienced by the different sensors and the sensor modalities, which is basically what a sensor fusion module does. And it also meant that velocity estimations were based on frame-by-frame detections and the differences between those detections. Then came the second generation of pipelines, which were mainly motivated by runtime performance considerations on the abandoned platforms. If we wanted to process more cameras or higher resolution cameras, we wanted to run neural nets more efficiently. And for this reason, in order to eliminate the need to run the neural network backbones a couple of times, like once for forward camera object detection, once for forward camera lane detection, once for back camera object detection, and once for back camera lane detection, we could combine at least the processings that were executing on the same camera images and create multi-headed neural networks. So we had one neural network consuming one image, which outputs multiple types of outputs in a single step. And this was very good for runtime performance reasons, but also it was suspected that it supports the execution of this task by informing the processes about each other, meaning, for example, if the object detector sees a row of vehicles, then it might infer that there is a lane in there, even if the lane markings are not visible. And then after Tesla started to talk about neural nets, which are able to generate top view or so-called bird's eye view representations from a multi-sensor input in one step, everybody started to use this kind of processing. In this case, everything is handled in one shot. So it basically means sensor data goes in, multi-sensor data goes in, and the world representation is output. So it seems very simple. And in this case, taking this one step further, if we provide multiple frames to the neural net from the different cameras, as well as we supplement it with radar data, it can very well estimate the velocities directly and attach it to the objects, as opposed to estimating the vehicle speed from the subsequent object positions. This means that in such an architecture, no explicit sensor fusion module is needed. But it also means that we have to create training data with the same structure, expected inputs and expected outputs. So based on these approaches, subsequent approaches, there is some lessons to be learned. First, when we started this journey in aiMotive and many companies during those years, most neural network-related literature was quite generic. So we had generic object detection and object classification networks, and I'm pretty sure there are use cases where recognizing donuts or apples is useful, or when separating dog breeds from each other is useful, but automated driving is not one of them. Also, the KPIs we have been using were quite generic and often even misleading, because KPIs have to drive the development efforts and focus where we have to improve. And I show you some examples how these can be misleading. So this is a typical confusion matrix. For those who don't know what a confusion matrix is, it's basically here in the columns, we can see the real class of the objects which are constituting our test set. And in the rows, we can see what the neural network thought the object class is. So based on this, in the diagonal, we can see those instances which have been detected and classified correctly. And outside the diagonals, we can see those test cases which somehow went wrong. Now, from this specific confusion matrix, which, by the way, comes with made-up numbers, so this is not a real example, we can see that the problem here is that buses and trucks are often mixed up with each other. And also we can see that bikes and motorcycles are often mixed up. Now, in case we have an object tracker after the recognition algorithm, it is indeed useful to know whether we are looking at a motorbike or a cycle, because these objects are capable of different velocities and different accelerations. And also, separating buses and trucks has its purpose, because we saw that it increases the confidence of the users in the system. If they can see on the visualization, look, I can see a bus in there, and yeah, I can see a bus on the screen. So it really improves the feeling that the system indeed knows what is happening around it. But the question is whether is this really such a big problem as classifying pedestrians as road surface. Now, of course, we don't want to hit pedestrians or cyclists, so indeed, we have to very much focus on such occasions, even if they occur only once. But this is not immediately apparent from a confusion matrix. The other way around, if we just see random objects as opposed to seeing the road surface correctly, that's a huge problem because that would result in false braking. Now, some of these misleading results can be eliminated if we reduce the number of object classes. So that we, for example, if we merge buses and trucks, we don't have any further misclassification problem. But then the question is how much we can reduce the number of classes to be meaningful and in order to avoid misleading us. There are also approaches which weight the elements of these confusion matrices according to the severity of the event that might occur if such an event happens. And that's actually a very good approach. Another very simple example for traffic light classification. Here, if we just look at the sheer numbers, we can see that we have a problem with mixing up the red light with the yellow light. But is this really as big problem as seeing the red light as a green light and then going in an intersection when we are not supposed to? Another example from the segmentation network world. When semantic segmentation networks have been evaluated in the literature, the metric that was used was typically intersection over union, in which case all pixels have exactly the same weight. And if you look at the sheer numbers, you might miss the point that not necessarily all pixels are equal from the use case point of view. So if we look at these two examples, do we think that the top part of the object matters as much as the bottom part? Because if we project these pixels to the 3D world, one would result in a distance error, which would in turn propagate to a diff speed error during later processing, or the other error, which basically introduces an error about the height of the object. Now, which one would you care about more? And the metric just hides this. So the lessons learned from all this is that specific use cases require use case-specific solutions and use case-specific KPIs. So what is in the literature is nice as a baseline, but have to be fine-tuned in order to measure what really matters. Another takeaway is that we should really create neural nets which output what we are really interested in, and not what we think that the neural network can or cannot do, or what we can find in the literature. So for example, as opposed to asking the neural net to classify pixels in an image, we can get much better results by asking for the distance of objects directly, like you've seen in the third generation perception pipeline example. Or as opposed to asking for subsequent positions of objects and then deriving those to get diff speed of the objects, why not ask the diff speed directly? Because if we do that, we can get much better results. If you think about an adaptive cruise control situation, the differential speed is what really matters, because if we want to have a smooth ACC operation, what we care about is really the differential speed, because the actual distance from the vehicle is not so important. We want to maintain the distance, whatever that distance is, but it doesn't matter if the other vehicle is 10 centimeters away or not. Now, one might ask that if the advice is to create neural nets which do exactly what we want, then why not create a neural net which would just input all the sensor data and output steering commands and acceleration and deceleration commands. In fact, this was already done. It's called end-to-end learning, and there is a very nice paper from 2016 describing exactly such a system. Now, those of my colleagues who were fortunate enough to be able to try this system in an actual vehicle were not impressed. And why is that? If we look at the paper, we can see that the network architectures back then and the network architectures we use today, today we have much more elaborate network structures. Indeed, neural networks are created piece by piece, backbone by backbone, head by head, trained separately, cut apart, stitched together, pretty much like surgery. And also the network components and the overall networks are much deeper and much bigger today. I also wanted to mention some spin-off projects from aiDrive. So aiMotive company was created with the purpose of creating a self-driving software stack which was called aiDrive. But on the way, we started several internal projects supporting the development of aiDrive. A good example is aiSim, which was meant to be an internal development tool in order to enable us spend less time on the road and to enable testing new features with a combination of simulated and real testing. And we really consider this as a competitive advantage that we have a simulator which is developed in-house according to the needs of aiDrive. And indeed it was, because it enabled us and still enables us to do one master merge every day for new features, or even two master merges every single day. But we kept aiSim for ourselves until the point when, well, we have been pitching aiDrive to different potential partners and customers, and when we mentioned that we have a simulator built in-house for testing the functions, they started to ask questions about aiSim, sometimes even more than about aiDrive. And based on the push of the sales team, eventually aiSim was opened to the outside world. And it is now used by the aiDrive team as well as several other companies and groups to simulate and test their solutions. So it basically enables real-time simulation of cameras, radars, lidars, as well as place these sensor-equipped vehicles into situations in urban highway and parking scenarios. And it also comes with several sensor models, which can also be extended by the users through the API. And as far as we know, this was the first simulator in this domain which received ISO 26262 tool certification. But then there is more. They say that besides every successful person, there is a supportive counterpart somewhere, and I think this is true for automated driving stacks as well. For every successful autonomous driving stack, there must be a supportive data pipeline somewhere. And this is exactly what aiData is, which was an internal project for a couple of years working alongside aiDrive, until we realized that the data pipeline can indeed be useful for others than the aiDrive development team. aiData basically enables the capturing of calibrated and synchronized multi-sensor data on the vehicles. And it comes with tools for automated annotation and quality checking, for manual annotation and quality checking, and also data management tools which enrich the captured data so that the AI researchers can query those video sequences that they are more interested in alongside the other sensor data and the metadata that was captured with it. And I can say that since we have automated annotation, we spend much less on manual annotation. Even though automatic annotation is never perfect, well, I can tell manual annotation is never perfect either. So we have to have measures in place to compensate for that. And the advantages of developing these tools under the same roof is that the tools and the teams which are developing these tools can very well support each other. So in the case of AI Drive and aiData, AI Drive supports the aiData activities by enabling the simultaneous execution of the algorithms and recording the sensor data at the same time on the ECU, meaning that we don't have separate recording boxes in the vehicles. So everything is handled by the same software, which enables a seamless flagging of the interesting events inside the AI Drive. So if there is a developer who wants to collect data from a specific occurrence, they can implement flagging mechanisms inside the AI Drive, which would be then, the flags would be introduced in the data stream, so that when the vehicle comes in, the specific sequences can be processed automatically and filtered afterwards. Then what the aiData tools do for AI Drive, first, enriching the data with external data sources like weather and map data, as well as executing algorithms which, because of their runtime, could not be executed in the vehicle. So we can do post-processing of the sensor data, one of which is actually automatic annotation, which creates the 3D bounding boxes and the attributes of these for the scenes in question. Also, aiData contains a synthetic data generation unit, which we call aiFab, which is basically relying on the aiSim rendering engine to generate synthetic sensor data, but without real-time constraints in this case. So for example, we had an example when an automated emergency braking function was failing, and we saw that the reason is that there is something wrong with the recognition of very close vehicles. Turned out that it is caused by the lack of training data in those situations when the other vehicle is very close to us, because this is something you typically don't want to record in a highway environment. You can record it on a test track, that's fine, but it's even simpler to make up for this gap with synthetic data, and that's exactly what we did, and we could fix the automated emergency braking function. aiData and aiSim, they also work together very closely. So as I said, aiSim provides the rendering engine for the synthetic data creation activities of aiData. But what aiData can do in return is metrics-based automatic refinement of sensor simulation and scenario parameters. What this means? If we run aiSim in conjunction with AI Drive, and we have a real scenario, and we have an exact replica of that scenario in simulation, we can tap the output of the recognition algorithms and compare the difference between those outputs with the AI metrics component of the aiData toolchain. Meaning, we can measure the difference between how the recognition algorithm sees the world in the real case and in the simulated case. So, which basically ends the debate about how realistic the simulation should be or how to make it more realistic, because from the perspective of the recognition algorithm, it's black and white. So it's really useful. But in order to do this, we need to have what some people call a digital twin. In our terminology, we call this resimulation. So we can do resimulation of real-life scenarios. And let me show you an example. So in this case, the AI annotate element of the aiData pipeline automatically annotates the elements of the scene. With the aiSim toolchain, we can generate a synthetic map from HD maps. And then for every vehicle that was recognized by the auto-annotation pipeline, we place a vehicle, and then we basically pull it on a string based on the positions that have been recognized. So once we have this scenario, and vehicles end up in the correct positions because of the GPS coordinates, we can run this simulation over and over again, but we might even change the parameters of the simulation. So this resimulation basically contains of two parts. The first part is the automatic annotation, in which case multi-sensor data goes in, And what you can see on the right-hand side, dynamic objects are indicated by the green bounding boxes, while static parts of the scene, which in this case mean lane and road boundaries, are indicated by the blue lines. So once we have all this, we can generate a scenario based on it. So we practically put the dynamic objects on top of the HD map that was created, and then we can replay this directly in AI Sim. Yeah, as it was pointed out, Stellantis acquired aiMotive end of last year. And shortly after the acquisition, Mr. Carlos Tavares, who is the CEO of Stellantis, visited us in Budapest and tested the vehicle and met the teams, and we explained what we are doing. And we also took this opportunity to interview him about how he thinks aiMotive will contribute to the goals of Stellantis. So I will let Mr. Tavares speak.
Well, aiMotive is going to contribute a lot. First, because the DNA of aiMotive is about innovation, about smart thinking, agile mindsets. And we expect that aiMotive will help us to accelerate and contribute to what we are already trying to do. So by bringing aiMotive to the Stellantis family, we expect acceleration, and we expect more competitiveness for the next levels of automation. For the current developments, it's an acceleration factor for going faster to market and using the bricks that have already been developed by aiMotive. And for the next levels of automation, we expect aiMotive to have a leading role in finding the most efficient way to get there, and also, to a certain extent, the way that will allow us to let a high number of customers enjoy those systems, which means affordability. If we want to have a significant number of our customers that can enjoy the ADAS and the automated systems, then it has to be reasonably affordable. And that brings us to a smart way of generating the performance with a bill of materials that is absolutely customized to the performance that we want to deliver. I think in all of this, we see innovation, agility, experience playing a key role to set the right direction for Stellantis, and we are counting on aiMotive to lead us there.
Okay, so what we should know about how aiMotive operates inside Stellantis. aiMotive is now a fully owned but independent subsidiary of Stellantis. And the intention is to keep it that way, to keep the independence from Stellantis and keep the startup way of working, which basically means that when we want to be aiMotive, we can be aiMotive, and when we want to be Stellantis, because that's better in the given situation, we can be Stellantis. And while aiDrive is now exclusive to Stellantis, the other tools, aiData, aiSim, and aiWare, these are still available to anyone who would like to use them. And the Stellantis position is that these products are strengthened by the feedbacks and the requirements coming from the other companies. But of course, we already implemented Chinese wall mechanisms to avoid information leak from these other clients to Stellantis or between each other. Of course, Stellantis teams already started using aiSim and aiData tools, and also aiWare is being discussed. For simulated testing, for auto-annotation, and also for querying the annotated data that they capture and also that we provide. But also, aiData and aiDrive profits from the scale of Stellantis. So we can rely on the connected vehicle fleet, which has the scale that we've never had, the compute infrastructure, which is readily available, as well as the experience of the multiple brands and the multi-continent team. So we are very happy to become part of this big family and operate in this way. And with these thoughts, I thank you for your attention. And if you have any questions, then please ask now, or feel free to find me later during the day. Thank you very much for your attention.